Okay, good morning. I wanted to take just a couple minutes and talk about some of these problems from yesterday, 17 through 22 here, and I've got it on a split screen right now so that you can. So eventually we're going to use both of these, but I'll open this up a little bit. Um, these questions use the central limit theorem to find the mean and the standard error of the mean of the indicated sampling distribution, then sketch a graph of the sampling distribution. And sketching graphs is a little bit of an outdated concept. It's more important for us to know what effect this process has on the graph. And we can illustrate that really well if we look in here at graphing these on Desmos. So let's jump down here to number 18. The number of eggs female houseflies lay during their lifetimes is normally distributed with a mean of 800 eggs and a standard deviation of 100. So we're going to start and let's do a normal distribution for that. So if we come in here to Desmos, we click on the keyboard, under functions, distribution is normal distribution. Now you could have just typed that in and it would have recognized it. And it needs two inputs. It needs a mean, which we saw in our question, which was 800. And it needs a standard deviation, which was 100. And we close our parentheses, and it will make a graph. And I'll really quick blow this up a little bit so we can see this a little better. And because our mean is so high, it's all the way out at 800, we're just going to click this button right here that says Zoom Fit. Sorry, we're in the library. There's a lot going on right now. And here we go. Here's our normal distribution. Pretty simple. Whole group of students just came through, so it got kind of loud for a second there. So here's our normal distribution. Keep in mind things you should know about it. Mean is always in the middle of a normal distribution. Standard deviation 100 is our inflection points. So if we see this is 600, 800, our inflection point here is at 700 because it's one standard deviation below and one standard deviation above. And that would be our inflection point. That's where our curvature of our graph changes, okay? So when we do this process for the central limit theorem, where we're taking a sample of data points instead of a single data point, random samples of size 15 are drawn from this population. We're going to put a second normal distribution. The mean doesn't change. That always stays the same. However, what will change is instead of having 100 as our standard deviation, we'll have 100 divided by the square root of our sample size, which is 15. And we can already see this graph has popped up here in blue. So what actually occurs here is that when we divide this 100, the standard deviation, by any whole number greater than 1, you're going to get a smaller resulting standard deviation, which means this area in here between the inflection points, which we're at 700 and 900, it's now been pulled in closer to the mean. And the end result of that, remember, the area under every normal curve is always 1 or 100% of your population. So by pulling those in closer, you've really tightened your distribution up and made it a lot taller. Now we'll zoom out here a little bit. Let's get an idea of how high we have to go here. Pretty high. So we'll just zoom fit it to the blue graph and then we'll see. There we go. So your original bell curve is now actually very flat. I'll go back to that. There it is. And your new bell curve, because we have a smaller standard deviation, which is now pulling our data closer in towards the middle, is much taller and much narrower. Okay, so you don't have to actually sketch these. We have these powerful graphing tools at our disposal. We might as well use them. But that's the drastic effect that taking a sample of 15 data values will have on your bell curve as compared to examining probabilities for individual data values. If you're looking for probabilities of individual data values, you'd be using this bell curve down here. if you're looking for probabilities for samples of data values, samples of size 15, you'll be using this value here. This is question number 18 from the work you did yesterday. I did post a screenshot yesterday. I did the same thing with question number 17, but it didn't have an accompanying video. I'll post this video today. I'll post a screenshot of this as well so you can see what the inputs are. Again, normal distribution is under the functions. There's a couple of them. There's functions for statistics, mean, median, mode, quartiles, standard deviations, all kinds of different things here, combinations and permutations. There's also distributions. We've done binomial distributions. We've done Poisson distributions. Now we're doing normal distributions. There is the possibility to find a cumulative probability. So you could answer questions in here, just like you could when we had normal distributions. Find a cumulative probability. If you want to know the probability of a female housefly laying less than 750 eggs, you would simply put 750 in for your maximum value. And I believe it actually shades it as well. So you could see that area is now shaded in. The probability of them laying less than 750 eggs is given to you. So it's very simple to use Desmos. Desmos is a really, really powerful tool. Let's say we wanted to know between 750 and 850. We could do that calculation very easily, putting in our upper and lower values. Desmos is really, really nice for this. I know we've been using Google Sheets a lot, but as far as this is concerned, Desmos is really, really good. So you can go ahead and take a look at this. I will screenshot this and post it, and I'll also post this video. So thank you, and email me if you have any questions.